This is Chemistry Unit 9, Stoichiometry. For the introduction, stoichiometry is the calculation of quantities in chemical reactions. It combines a lot of concepts we've already talked about: chemical formulas, moles, balanced chemical equations, and some other topics that we've covered so far in the course. Stoichiometry is the study of quantitative relationships between the amounts of reactants used and the amount of product formed by the chemical reaction. I'm going to start with some non-chemistry examples. And so a couple non-chemistry examples would be a tricycle or a skateboard. A new tricycle comes with some assembly required, and it has a lot of parts. Every part is pretty important to the function of this particular tricycle. It's going to have a frame. It's going to have wheels, handlebars, a seat, and pedals. Now, a tricycle may have other little pieces on it, but these are the main functional things. If you only have one of each of these components, you're not going to build a tricycle. If you want to build a tricycle and you want to make one that functions, you have to have the correct quantities of each component. And here I have basically a balanced equation representing what we need to make this tricycle. One frame plus 3 wheels plus 1 handlebar set plus 1 seat plus 2 pedals yields 1 complete tricycle. So a couple of questions. How many tricycles could be built from 14 pedals? Now we're only considering the number of pedals here. And this is how we would set it up. 14 pedals. And if you look up here, we need 2 pedals for every 1 tricycle. And this is really a dimensional analysis problem because pedals would cancel out and leave you with tricycles. 14 divided by 2 essentially is what we're doing. And these basic examples, non-chemistry examples, you can mostly do in your head. Another example, how many tricycles could we build with 42 wheels? Same idea. 42 wheels. We know that a tricycle has 3 wheels. For every 1 tricycle. Again, wheels would cancel out and leave us with tricycles. 42 divided by 3. Based only on the number of wheels, you could make 14 tricycles. We could talk about skateboards, and a skateboard requires 3 basic components. They're fairly simple. There is a deck, there are wheels, and there are trucks. The trucks are the axles. A functional skateboard requires the following. It needs 1 deck, it needs 4 wheels, it needs 2 trucks. All of that yields 1 skateboard. So if you find 20 wheels in a box of skateboard parts, how many skateboards could we build? Again, considering only the number of wheels here. This is a dimensional analysis question. And this goes back to almost the beginning of the year when we talked about dimensional analysis. Everything in this unit has to do with dimensional analysis in some form or another. If you are rusty on dimensional analysis or maybe struggled the first time, we should look back at the dimensional analysis unit. It's in the unit called Analyzing Data, and maybe practice. But as far as this unit goes, you're going to get a lot of dimensional analysis practice. So hopefully it will catch up with you if you're struggling. So this dimensional analysis question, if you find 20 wheels in a box of skateboard parts, how many skateboards could we build? And so we see from this balanced equation that we need 4 wheels for every 1 skateboard. We put wheels on bottom because it's the unit we started with, and by putting it on bottom it will cancel. And it leaves us on top with the units that we want, and that is skateboards. 20 divided by 4. Could make 5 skateboards based on the number of wheels. This is the basis of stoichiometry. So you understand this from a real world perspective. Now we just have to take what we know how to do and apply it to chemistry terminology and concepts. We just came out of the balancing equations chemical reactions unit, but there's a quick review on balancing equations. Remember, a chemical equation represents a chemical reaction. And the equation, the purpose of the equation is to make sure that what's happening in the reaction in the real world is reflected on paper. A balanced chemical equation shows the chemical formulas, and they're written in a ratio that obeys the law of conservation of mass. Everything in this course has to obey the law of conservation of mass. Chemical equations are balanced by writing coefficients in front of chemical formulas. A balanced chemical equation must have equal numbers of each element in both the reactants and in the products. I compare a balanced chemical equation to a recipe. A chemical equation requires a recipe. With the recipe, we can add the appropriate amount of each reaction. A lot of times, we have to follow it for a reason. We don't want to waste laboratory chemicals, so that's one thing. Or even worse, we don't want to contaminate products with excess reactant. Like a cookie recipe. If you follow the recipe very closely, you'll have delicious cookies. If you don't follow the recipe, let's say you put in 10 times more of the baking soda than you're supposed to, you're going to have cookies contaminated with excess reactant. They're going to taste disgusting. They're going to taste like sodium bicarbonate. It's not going to be good. They're going to be soapy almost. You also need to know how to control a chemical reaction. We don't want to create a possibly runaway reaction. If you add way too much of two things and it gets out of hand, it could be dangerous. So the cookie recipe. If you add too much of any one substance, it's going to ruin the cookies. Any deviation from the recipe may yield cookies that are burned, too hard, contains too much sodium, tastes like soap, etc. The recipe requires a specific ratio of ingredients to yield good cookies. You might say, well, I really like things that are sweet, and so I'm going to add twice as much sugar as the recipe calls for. They're probably going to burn and be really hard. If you don't follow the recipe, every cookie recipe requires a little bit of salt. Just a pinch of salt brings out the sweetness, but if you put a little bit too much salt, they're going to taste like sodium. They're going to be salty. That's no good. Adding too much of the baking soda tastes like soap. The recipe cannot be ignored. Just like in chemistry, we cannot ignore the recipe. Continuing from the previous unit, we're going to use the Haber process quite frequently, and this is, remember, the industrial production of ammonia from its elements, the synthesis of ammonia. To put it in Unit 8 terms. The synthesis of ammonia. We've balanced this a bunch of times before. If you consider the nitrogens, they need to be equal. 2 over here, 1 over here. Now they are 2 on both sides. That makes 6 hydrogens on this side and 2 on this side. A 3 here makes 6 on both sides. The balanced chemical equation has to obey the law of conservation of mass. This means the number of nitrogen atoms in the reactants must equal the number of the products. The number of hydrogen atoms also same in the reactants and products. In this balanced equation, 2 nitrogen atoms and 6 hydrogen atoms are present in both the reactants and the products. Putting it in terms of mass, the mass of the reactants and the mass of the products must be equal. Now these numbers I'm going to use are reflecting the molar masses. So for nitrogen, the molar mass is 28.0 grams per mole. Hydrogen is 2.02 grams per mole. And ammonia, 17 grams per mole. That's where these numbers are going to come from. And I'm going to use these numbers along with the recipe to figure out how much we're going to put together. So I'm going to put in, nitrogen, 28 grams times 1. 28 grams of nitrogen. And then for hydrogen, let's just call this 2 grams. 2 grams, and I need 3 of those. So there's 6 grams. Then I would expect, putting in 28 plus 6 grams, 34, I would expect to get 34 grams of ammonia. The total mass of the reactants is 34 grams. The mass of the product is 34 grams. No matter was created, meaning that the mass of products were greater than the reactants, and no matter was destroyed, meaning that the mass of the reactants was greater than the products. In addition to the Haber process, we're going to use 3 chemical reactions for most of this unit. So the first one is the decomposition of water. Now remember, decomposition is where we have one reactant breaking down into two or more smaller products. And so if it's the decomposition of water, water is our reactant. And it is breaking down into its only option is elements, which would be hydrogen and oxygen. And these are both members of our 7 binary molecules. They cannot be by themselves. I have no bright or clever friends. And these will both exist as gases. So here's the decomposition of water as a skeleton equation. It's not balanced. And so the oxygens are causing us a problem. And so in order to make both sides equal, we have to put a coefficient of 2 in front of the water. That fixes the oxygen issue, but it creates a hydrogen issue. So now we have 4 in the reactants and only 2 in the products. Adding a coefficient of 2 to the hydrogen will complete the balanced equation. We're going to use this one frequently throughout the unit. The reason we're balancing it now is so that whenever we need it, if we don't just do it in a couple seconds really quickly, we have a reference point where we can look back and say, yes, at this point it was balanced. These are the coefficients we need to know. Then the formation of rust. And the formation of rust, put in more chemistry terms, is the synthesis of iron 3 oxide. And remember, synthesis is when you have 2 smaller reactants creating one larger product. And so we have iron, which is a solid, plus the oxide comes from oxygen, which remember is one of my diatomic molecules, oxygen gas, creating iron 3 oxide. So remember what iron 3 oxide means. That 3 here is telling me about the charge of the iron. It is not telling me about the quantity of iron atoms. Iron 3 plus, and oxide is always 2 minus. And remember, switching the charges gives us Fe2 of 3. And this is going to be a solid. You're familiar with it. It's brown. It kind of crumbles at times. It's not very strong. Here's our skeleton equation for the formation of rust or synthesis of iron 3 oxide. Now it needs to be balanced. The irons are not equal and the oxygens are not equal. In this situation, it's best to start with the oxygens. You have an odd number in the products, an even number in the reactants. Best thing to do, least common multiple, make it 6 oxygens. So a coefficient of 3 makes 6 oxygens in the reactants, and a coefficient of 2 makes 6 oxygens in the products. Now for the irons, I have 1 in the reactants, 4 in the products. Giving iron a coefficient of 4 will fix the problem. And now we have a balanced chemical equation. The third equation that we're going to balance here is lead 2 nitrate plus potassium iodide yields lead 2 iodide plus potassium nitrate. This is a double replacement reaction. I have two ionic compounds creating two different ionic compounds. So the first thing I'm going to do is up here, write the atomic symbols with the charges, just so we can see it. This is not a required step, but it's helpful. So lead 2 tells me lead 2 plus. Nitrate, if you don't remember it by now, you can look back at the ionic compounds unit. It's on the last page. Or you could even check the solubility rules table in the chemical reactions unit. It's also there. NO3 with a -1 charge. When you cross the charges or switch the charges, you end up with PB parentheses NO3 2. And that's aqueous. Plus, next reactant is potassium, it's group 1, iodide, group 17. Yields lead 2 iodide, so here's my lead 2. You'll notice the charge did not change. And iodide, charge did not change here either. Switch the charges. And this is my precipitate. And then we have potassium, still group 1, nitrate, still the same formula and charge, KNO3. And remember from the last unit, alkali metals tend to be soluble, nitrates are always soluble. This one is aqueous. So balancing, we have 1 lead on either side, that's fine. Here we have 2 nitrates, here we have 1. So let's put a coefficient of 2 to fix that. That makes 2 potassiums, but only 1 over here. Coefficient of 2. And then we have 2 iodines and 2 iodines. And now we have a complete balanced equation that we can use going forward.